Hi, I'm Mrs. Sheets from Maplewood Elementary in 6th grade. We are learning about mechanical energy. I'm going to blame that on you.
That's probably the best introduction we had. Mechanical energy. Thank you, Mrs. Sheets. And who's going to help you with this? What's his name?
Mr. Crosslin.
Hey, thanks a lot for that energetic introduction, Mrs. Sheets. When you talk about mechanical energy, that was filled with it. So today we're going to be talking about mechanical energy. Now you might think it's going to be really hard, and it might be, or it might be really easy. You see, mechanical energy has to do with two types of energy. One of them, which we just saw, kinetic energy, when Mrs. Sheets demonstrated a ball coming right at me. Thank you very much. And the other one is potential energy. So let's take a look at both of these. All right, so mechanical energy, boys and girls, is really two things. It's potential energy. You can write this on your notes. Potential energy plus kinetic energy. Okay, these two things together we call mechanical energy. Got that? Potential energy, kinetic energy, together they are mechanical energy. All right, so let's look at both of these first. So potential energy really means what? It's what kind of energy?
Energy stored.
Energy stored, thank you. So when you think of energy stored, potentially, we're talking about stored energy, okay? And when you're thinking about kinetic energy, it's the energy of what?
Motion.
Motion. Excellent, guys. Motion. Okay. Now, just a little side note here. There are three types of potential energy, and we're only going to really talk about one today. One type, you just had lunch. Lunch, that food that's inside of you right now, and it's being transferred. It's being transferred into chemical energy. It's potential energy that is chemical. You know, food is that way. So is burning wood or gas or coal, anything that burns. Anything you can eat that gives you energy is chemical potential energy. The other type is elastic. Elastic potential energy. Okay, so we're talking about elastic potential energy. And what type do you have?
I have elastic energy, just like a spring.
So when you squeeze it, it pops back?
Yes.
Okay, that's one type of elastic energy. The other type is like a rubber band. You can help me with this one. So I know, trust me.
Like go on one.
Hold this. No energy, right? So let's give it some elastic potential energy. On the count of three, let go, okay? So that way it snaps this elastic. It's stored. Let's see, kinetic. 1, 2. You've seen my video before.
I have.
Let's try it again. This time you count, okay? No energy? Go, you describe it. No energy, say it.
No energy.
And what is it?
Elastic energy.
On 3, you let go.
1, 2.
Thank you.
We're even.
We're even. Not really, I'll get away. Okay, so this is elastic potential energy. So that's a second type. We're not going to mess with that today, but what we are going to do is the kind that I really like. This is a cool word. It's a cool world also, but this is a cool word. And it is gravitational. Everybody say it like that.
Gravitational.
Gravitational. Gravity, right? So gravitational is an attraction, a pull. It is a weak force, but it's everywhere. Now, Mrs. Sheets and I, we want to tell you something. And in case you get on TV, on Jeopardy, or Smarter Than the Fifth Grade, or Who Wants to Be a Millionaire, or whatever, if they ask you a question about gravitational potential energy, about gravity, and before you answer, phone a friend, call me so I can help you make some money, and me a little bit maybe, or Mrs. Sheets. For example, I let go of this, 3, 2, 1, and gravity pulls it to the earth. 3, 2, 1, gravity pulls. It happens every day. Hey, it's a law. Don't live without it. My question is this. If you're in a spaceship and you're flying around in outer space, is there gravity? Before you answer, Remember, phone a friend because you may need help on this one. Is there gravity in outer space? And the answer is
Yes. Yes.
I mean, before you finalize your answer, think about the sun. If the sun is the size of me right here, if I'm the sun, the Earth is not even as big as this ping pong ball. So the Earth compared to the sun is pretty small. But the gravity of the sun holds the Earth in the orbit, just like we studied in the first unit, right?
Yep.
The moon going around the Earth is held by the gravity of the Earth. So my question is, if we did not have gravity, would all these things stick together in space?
No.
No. So the answer is, is there gravity in outer space? And the answer is
Yes.
yes. Now, it looks like when you see something falling like this, when you see a guy in space or a woman in space that are floating around, what you don't see is that they're actually moving hundreds, if not thousands of miles an hour. The whole spaceship is moving. And so they are actually in a free fall. It's kind of like they're falling. For example, you get in an elevator, a big tall building, 400, 500 feet tall. You cut the elevator and you're flying down. For about 3 or 4 seconds, you're going to have a great time. You're going to be free fall, having a great life. It's going to feel like you don't have gravity. But remember, it's a law, and gravity will come rushing back at the last second when splat. So,
Your law of it.
life as you know it has come to an end. Let me help you explain this a little bit better. Okay, so this is really quick. So here's the Earth, right? Here's the Earth, right? And if you have, let's say, a cannon right here, and you shoot the cannonball up, it's going to be propelled by its gases. It's going to go ding, 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 and crash somewhere on Earth, right? And now if you shoot it harder, it's going to go ding, 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 and over here, right? Well, a rocket, or if you do it to a cannonball, if you shoot it hard enough, it's going forward and it's falling also. If you shoot it hard enough, ding, 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 it can keep going and it can fall and come all the way back here. And if you shoot it hard enough and fast enough, it'll keep going, so it's actually falling and going forward and being pulled down. And this is what spaceships do. And that's what when you orbit the Earth. Got it? Memorize it? Cool. All right, so let's start with, to understand mechanical energy, we're going to have to add these two together. So we're going to have to find out what they are first. So let's look at potential energy. And so I'm going to call that PE from now on, okay? Potential energy. And there's a formula for it. It's really not that hard. Potential energy, the formula is height times mass, or how tall something is and how heavy it is. So height will be in meters times mass, which will be in kilograms. Mass times meters in kilograms. All right, let's do a demonstration. Okay, so you're my volunteer? Okay. All right, so we're talking about gravitational potential energy, right? And so we're going to see that effect on you, right? All right, so why don't you go ahead and lay down on the ground here? Okay, so we're going in the front. So we got our friend right here. I'm going to drop this on your stomach. So make your stomach goes out of the way there, man. All right, this is from zero height. This is 1 kilogram, right? On the count of 3, 1, 2, 3. Didn't do much, did it? The height is 0. 0 times 1 kilogram. So what's 0 times 1? Zero. That was 0 joules. We measure this energy in Joule, joules, right? So 0 times 1, no potential energy, all right? Let's move it up 1 meter, okay?
Yeah.
1 meter times 1 kilogram, 1 times 1 equals what?
1.
1. Let's see the effect of 1. Make your stomach tight. 3, 2, 1. Gravitational potential energy. Nice. A nice sound thud. There you go. How did that feel? Talk to me.
Not that much.
Oh, not that much. How can we increase?
Higher.
Okay, let's go 2 meters. 2 meters. Now we're using the same kilogram, but now it's 2 times 1 kilogram. How many joules?
2.
2.
Rest in
Are you
peace.
ready?
Rest in peace.
3, 2, 1. Oh, I heard it. Did it feel different? Listen to the man. Talk to me.
No, it wasn't different.
Wasn't
It
different.
felt the same. I salute you, man.
What's wrong with you?
Force into it so it can actually hurt.
Okay, first, that has no feeling.
Try a
That feels
basketball.
like that.
Yeah.
And that feels like that. Okay?
It
Now,
doesn't.
you notice I am not using chemical energy.
You should.
No,
try.
no, I shouldn't. Let's go 3 joules, all right? 1 meter, 2 meter, 3 meter. Ready? 3 times 1 kilogram. How many joules? 3.
3,000.
Are you ready?
Yeah.
Listen quietly so we can hear the effect. 3, 2, 1.
It's a little harder.
A little lower. Okay. You want to go for 4?
Yeah, 4.
We're going for 4. Give me a chair, please.
Okay.
We're going for 4 joules of energy, right? So we are increasing the potential gravitational energy because we are going.
4.
Let's go for 4. Are you ready?
Yep.
I'll be at your funeral.
Any last words?
I'll be at your funeral.
Don't you dare throw up in this video. Here we go. 4 times 1. 4 meters times 1.
Face.
I'm not gonna hit your. I'm not gonna hit your.
Alright, let's go.
There we go. Don't you move. Don't be a chicken. Don't be a
I'm
science
not
chicken.
trying to let me hit me in my face.
Well, 3, 2, 1, and that was a mess. Do over.
Make sure you actually
Here we go.
hurt him.
Perfect. 4 joules.
Nope.
Here we go.
A little harder, a little more.
Okay, can you feel so you notice that another way we could do this is to increase the energy. Instead of going higher and higher, what else could we do?
Faster.
No, that would be putting another time. That would not be gravitation.
Use a basketball.
Farther.
Go get that bowling ball over there.
Oh my god.
No, we can't do a bowling ball, but if we use something that was heavier, had more mass, then it would increase the potential energy. So let's draw what we just did, okay? Well, your young man's name was what? What was his name? Okay, and so he's got his hair sticking out. I'm not too good at drawing kids, but anyway, here we go. I'll do my best. He had a funny nose anyway. And there's his chest, he comes down, and there's his leg, okay? And there's his hand here, okay? And he's kind of, All right, so right here that was a kilogram, right? Right? So if we want to find its gravitational potential energy, here we go. The height was 1 meter, that's 0 meters times 1 kg equals 0 joules, right? Then we moved it up to 1 meter. It was still a kilogram. So now it's 1 meter times 1 kilogram, kg, and so that equaled 1 joule. So now it dropped down, right? Then we went to 2, but it was still 1 kg. So it was 2 times 1 kg. It was 2 joules. Came down. And we eventually went up to 4 meters times 1 kilogram, and that equals 4 joules. So that's pretty easy, don't you think, at figuring those things out? So the higher we go, the more potential energy, and you could tell the effect each time, right?
Mm-hmm.
Okay, let's see if we can do that one other way. Okay, so I have here a piece of malleable clay. Okay, it's clay, it has no marks on it, so I put the clay down. Okay, and now I have a hard or a heavy steel ball bearing. And even let's try by the sound. If I just drop it, no potential energy. Here's a little bit. Listen to the sound. Now higher, listen to the sound. Higher. Can you tell the difference in the sound?
Louder.
All right, so maybe we can drop one at this height and we'll see the mark it makes in the clay. Ready? Gravitational potential energy turns into kinetic. 1, 2, 3, kinetic. Cool. Very cool. So we got a little mark right there. Okay, so you notice, I don't know if you guys saw this, but look, see that mark right there? That mark right there was from only about that high. Let's see what do you think the mark's going to do if I go even higher?
We're going to make it bigger.
We think it should have more energy. It should be bigger. So let's see here. Ready?
That's convertible.
I hope I hit it. Are we ready? I'm way up high. 3, 2, 1. Gravitational turns to kinetic.
Miss.
Nice. Let's take a look at it. What kind of mark it made. Wow, look at that. Much deeper. A much deeper mark here than it was here. More evidence that when you have more gravitational potential energy, you have more mechanical energy. Pretty cool.
This experiment could tell us how the craters on the moon were made.
Something must have hit the moon going pretty fast, or it must have been pretty big. So that is half of the story about mechanical energy, potential gravitational energy. The formula, PE equals height times mass. Let's switch to this side now. Now we're going to talk about KE. Anybody know what KE stands for?
Kinetic energy.
Kinetic energy. Write this formula down. We can find the kinetic energy of an object in motion. It is, this is kind of cool, it is 1/2 the mass times speed squared. Wow, that's a cool formula. 1/2 the mass times the speed squared. And you have been studying exponents, correct? Are we paused?
Wait, no.
Are we paused now?
No, it's on pause now.
Oh, we're not paused now. And just a moment for station identification. Are we recording? I'd like to introduce to you the brains behind the operation. Your first name is?
Sophia.
Sophia, and she's responsible for all the phone calls and all of the wonderful videotaping. Not really. Good job, Sophia. Shall we go on? Let me pause you. Thanks, Sophia. No, actually, so check this out. 2 times something, it would only be 8. But if it's an exponent, if it's 4 squared, that's the same thing as 4 times what?
4.
4 times 4, which equals 16. I want you to remember that when you have an exponent, it's much more than just multiplying, right? You agree? Okay, so let's go back to some kinetic energy, something moving. Something moving, for example, a large ball that is moving, let's say a ball that is 1 kilogram. So if we had a ball that is 1 kilogram, and it's going 10 meters per second, we could find out in joules the kinetic energy. So here's this ball that's flying down so what's 1/2 a kilogram would be 0.5 times, what's 10 squared? 10 times what?
100.
Times 10. So that's going to equal 0.5 times 100. Anybody know what half of 100 is?
50.
50. So that would be 50 joules. See how we did that? What if something, let's say, oh, this is going to be cool. So if something was 1 kilogram, got it? And it's going 10 meters per second, we can figure out that it's going to be 0.5 times 10 times 10, which is 0.5 times, which is 50. What if we double the weight? Let's double the weight. So let's do it 2 ways. Are you still with me, Sophia? Can you see it down here? Mm-hmm. Let's do it 2 ways. Let's first, A, let's double the weight. And then B, let's double the speed. Okay? So that equaled 50 joules. Now let's double the weight. So what's the weight?
1 kilogram.
So now it's going to be 2 kg times 10 squared. So that is going to be equal to what? 1/2 of 2 is what?
1.
1 kg times 100. So what does that equal now? What's 1 times 100? Duh.
100.
That's 100 joules, right? So if we double the mass, it went from 50 to 100. It doubled the joules. Is that simple? That makes sense, doesn't it? But watch this. This is the part that's really kind of amazing to me. Now let's leave it still as, let's not double it. Let's keep it as 1 kilogram, 1 kg, but we have to do half of that because that's the formula. Let's double the speed. So now it's not 10 meters per second. What is it? 20. And 20 meters squared. So 1/2 of a kilogram is 0.5. But now what's 20 squared? That's 20 times 20.
400.
That is 400, isn't it? And so 400, 5 goes into there. How much, if we multiply this, what is half of 400?
200.
200. Look at this, guys. We actually double the amount of energy here. It makes a lot more energy. Here, we only went from 50 to 100. Here, we went from 50 to 200. It quadrupled. It made it 4 times the amount of energy. So my question is this. If you want to increase kinetic energy, is it better to double the mass or to double the speed?
Double the mass.
Which one is it, do you think? Double the speed. When we double the mass, we only got a little bit of energy. When we double the speed, we got a lot. Let's see if we can demonstrate that. So we have two people that are giving this ball has kinetic energy. Now, we can increase the kinetic energy by changing the ball. If we made the ball heavy, but here, the way we really want to increase it, Mrs. Sheets, go ahead and hold that. Double your speed. Get ready, kiddo. Double your speed. Whoa! I'm telling you, she's a killer. Not the face. Now, make it normal speed. Let's see what it's like. Now, double the speed. Can you guys even hear that?
You can hear it bounce.
We hear it bounce. Do we dare quadruple the speed?
Yeah.
Do you have insurance?
I don't know.
All right, so let's even more speed. What's it
Without
called?
hitting her.
More speed. Oh, more speed. That's the more speed. Oh,
I don't want to hurt her.
you're right. Stop.
Yeah.
Because if we increase the speed, we're quadrupling the amount of energy. Now, this we should be like this. What are we going to do now if we decrease the mass?
Oh, it's not hurt.
It's going to hurt less. We hope it doesn't hurt at all. So let's do an easy line. And you see it's a lot less mass. And there you go. Okay. And so I want to show you one more demonstration, Sophia. Okay, so now we're going to change the arc of this. And so let's watch it go up and almost come back down. Ready? Up and down. Very nice. Up and down. Up and down. And ready? Up. And if we froze it right here, stop. This is a lot of potential energy because look how high it is. When it's over here, is that more or less potential energy?
Less.
Here is the most potential. Here is less potential, right? Same way here. Most, everybody? Most potential. What about here? Less. So it goes from less, more, most. Less, least. All right, so let's watch it again from more, most. Less, least. Ready? Bam. Bam. All right. One more. Now, for 1 second, when you throw a ball up, watch this. Ready? For 1 second, it's going up, kinetic, and then it has no kinetic energy, and then it comes down. Kinetic energy is the energy of movement. So for 1 second, for a split second, it has no movement. Ready? Watch it up there. Here we go. Ready? Did you see it? Did you see right up there? You hold it now. Try to hold it, throw it straight up slow. Bam, right there. Right there it stopped. So it went move, freeze, move. Got that? One more time. Let's watch, put it all together. We have kinetic, potential, kinetic. Kinetic, potential, kinetic. Let's see what that looks like when we draw it. Okay, so let's just take a look at what we just did here. We just did something kind of cool. Let me erase this right here and show you what I mean by that, all right? Okay? So, we had two people throwing a ball back and forth. And when the ball, this person was standing right here, throwing the ball up, okay, here comes the ball, here's the hand, and the ball's ding, 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 the ball leaves their hand at A, right? And the ball's going to ding, 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 and it gets right up here, and then it starts to come down to the next person getting ready, trying to catch the ball up here without getting hit. Okay, and so this person's a little scared, and the other person's kind of happy because the ball's like, okay, here comes the ball, right? Now, here's the ground. If we wanted to find the different energy, A or B or C, which one has the most potential energy?
B.
B, because that is the highest, right? Look out. That's the highest. So B has the potential energy of this one right here is about 20 joules, right? but it's slowed down. It's almost stopped. So what do you think the kinetic energy is of this ball right here? It's almost stopped. If it was stopped, it'd be 0. So it's probably, what do you think?
Like 3.
No, two, I guess 2. So mechanical energy is we add those two together. 20 plus 2, what is the ME? What's the mechanical energy right here? 22 joules, right? And since I said mechanical energy is going to be the same no matter what, here, not much potential energy, right? Maybe, what do you think, 8?
Yes.
So potential energy, because it's not very high, is 8 joules. So the mechanical energy we know is 22. So what does the kinetic have to be? 8 plus what equals 22? 16, right? 14? What is it?
14.
14 plus 8 equals what? 22, right? So this has to be 14 joules. Now let's go over here. If this is leaving their hands and the potential energy on this one, let's say the potential energy right here was a little bit higher. So instead of 8, let's make that 10, right? What does the mechanical energy have to be over here? It always has to be what? 22 joules. So what does that make the kinetic energy when it left the hand? What does it make it? 12. Thank you. So this is why I say this can be easy or hard. It's easy, you just add it. They have to equal the same no matter what. And that is mechanical energy. Hey, here's something you didn't know about your teacher, Mrs. Sheets. She is an expert Olympic ski jumper. You didn't know that, did you? Well, she is. In fact, let me show you. We're going to find the mechanical energy that she did on her last jump. You remember when you did that, Mrs. Sheets? Okay, she went down to the ski jump. And go ahead and draw this. Here's the ski jump. And it is 100 meters tall. Wow, I can't believe that. 100 meters tall. That's big. And here she is up on top of that. Okay? And she was wearing her toboggan. So she's getting ready. Here's her skis. Go ahead and draw this. Here's her toboggan with her, she's got her legs bent and her skis going. She's getting ready to jump. I can't believe she did that. 100 meters, right? She came down, and it started going down. She got faster and faster and faster, and then, of course, there was the jump. And then the track goes on down like this. Okay, so she's up here, right here. We'll call this A, all right? She's flying down here about B. Okay, got that? At the low point right here, we'll call this C. She goes flying off, and she ends up way over here, which is D, and then she ends up over here at E. Got that? So let's get your paper like this. I'm going to go ahead and draw her in. You go ahead and draw it in, right? She's going down here like this. There's her ski. There's her toboggan. Knees are bent. Down here. And then she flies up and she's going. This is the scary part. Can't believe she did it, but she did. She's up in the air here, flying like crazy. And eventually, she ends up back here. Okay, got that? Everybody go ahead and draw that. A, B, and C, D, and E. Got it? Here she goes. Okay? Sound effects are free. Okay, so we got Mrs. Sheets, and she's flying through the air, right? So let's do some of the heights. This here is 60 meters. Wow. Ready? This is one of the lowest points is 30 meters. Got it? Over here is 60 meters. Got it? And what do you think this is, boys and girls? 0 meters, right. Go ahead and get caught up. Okay, here's the one thing that's kind of, I want you to understand. Wherever we are, boys and girls, on A, B, C, D, or E, the mechanical energy is going to be equal to all of those. So that's the ME. And I can tell you right now, the mechanical energy on all of these is going to be 50,000 joules. All right? So here's what I want to know. Where is she the highest? A, B, C, D, or E? Which one? A. She's the highest at A, right? Where is she the lowest? E. So which one has the most potential energy? A. So let's call that PE. And here's a PE, potential energy. And here's PE. Go ahead and write that. And here is PE, potential energy. And here is PE, potential energy. You know, they say that math is the language of science, and that's what we're trying to do today. So we know that the mechanical energy at each stop of Mrs. Sheets jumping on this ski jump is 50,000 joules. And we know that this is where she is the highest. And this down here, what is the potential energy of her right here? 0. So this is where it gets real interesting. Are you ready?
Yep.
Well, here's where it gets real interesting. Let's see, I'll use the green. For this one, we needed also to know the kinetic energy. Now, is she moving at all right here?
No.
So, no movement. How many joules of kinetic energy?
0.
0 joules. Now, this is going to become now a simple math problem. If the mechanical energy at all of these, the ME, I should probably do that in blue, don't you think? If the ME for all of these is 50,000, what is her PE at this one? What does it have to be?
50,000.
What is it?
50,000.
It has to be 50,000. So she's got a lot of potential energy right here. Because when you add these two up, they have to equal 50,000. Got that? Now let's go to the very end of her jump. You got that? At the very end of her jump, she now has 0 potential energy because she's not high. She's on the ground. But is she flying? You bet. So what is her kinetic energy right here, do you think?
50,000.
It has to be 50,000, doesn't it? Because when you add those together, what do they equal?
50,000.
50,000. Because the mechanical energy, the ME, is always equal along the entire journey. So now it becomes something kind of interesting. I'm going to give you the rest of these, and I'm going to give you one, and then you figure them out. In fact, since B and D are the same height, they would have the same what?
Numbers.
They would have the same numbers. They would have the same.
Energy.
They would have the same
Potential.
potential energy. You got that? They have the same potential energy, which happens to be potential energy here is equal to 30,000 joules. You can figure out this one by yourself, because now you can figure that one.
It'd be the same.
And this 30 is half of 60. So you can figure these out. So let's take a break and have you figure it out. Okay, so you ready to fill these out? Which one are you going to do? D. So which one you want to do, the potential or kinetic? Let's do B first. What is the kinetic energy have to be right here, Dylan?
20,000.
20,000. Because 30 plus 20 equals 50. So that has to be 20,000. So you can fill, since that's the same height, go ahead and fill this one in. That has to be also 20,000, right? Got it? And if that's 20,000, what's the potential energy have to be?
30,000.
30,000. Very good, because mechanical energy is potential plus gravitational added together. Okay, so go ahead and you do C for me, all right? So what is the potential energy? It's half as tall, so what is it? What is it, class?
15.
15,000 joules. 15,000. All right, I'll take that marker and I'll give you the green one. So now, 15 plus what equals 50? 35,000 joules. Thank you. Okay, So at the beginning of this lesson, I told you that mechanical energy can be easy and can be hard. And now you see what I mean. It's kind of hard at first to think about it, but once you get it down, and I really want to say good luck on your next jump on this, your mechanical energy is all the same.